Alright, a video on magnetism. Should be anyway, mostly. So there's a channel called Applied Science, and you can't really see the guy, but he's over there. Very nice. Guy knows what he's talking about in a lot of ways. Really good videos, mostly. Well, generally I haven't found a clunker yet. You always learn something, and he does a lot of experimenting, does a lot of applied science, making circuits and such, and seems to cover a lot of different kinds of technology and such. So quite interesting channel, worthy of its popularity and all that crap, I would argue. Pretty straightforward, no gimmicks and all that crap, but okay. So I'm seeking somewhere where there's conversation about the fundamental assumptions of physics and ways to apply science or experimentation to attempt to find the truth. So I'll play the beginning of this video where he's just applying some logic, so to speak. Here's the logic of conventional physics anyway, in explaining how magnets convey their magnetism, or express it even, let's say. And yeah, I have fundamental disagreements, so I figured it would be worth pointing those out and contrasting the two perceptions of the reality. And they're really this is a strong perception that people have. I keep fighting over this subject where I keep pointing out how magnets don't have stuff swirling around them. There isn't a bunch of moving energy, all of that stuff, and this sort of illustrates that it's ingrained in all theory. But anyway, let's play it, and then I'll draw it.
In Applied Science, we're going to take a practical look at engineered magnetics. I've actually wanted to make this video for a long time because it's common to teach electronics with batteries and wires and make it very understandable. But for some reason, when it comes to magnetics, it's typically taught heavy on the math and the theory. So after watching this...
So, yeah, I would argue that his video just fell right into the same jargon. I mean, it fell right into mathematical analysis rather than practical analysis. Very quickly, so it did deteriorate into not very interesting.
Video, you'll have a really good conceptual grasp of magnetics.
So he didn't do any of that stuff with the green film stuff. That's a big piece of it.
And if you want to design your own transformers or motors,
he's got some really good equipment. He's got like a $5 million oscilloscope. I mean, touch screen, all kinds of. Oof.
This is a great place to start. So I mentioned batteries and light bulbs, and this is actually a really great place to start. Over here we've just got a D-cell, some wire, and an incandescent light bulb. And this is even taught in grade school level. I mean, it's pretty clear what's happening here. We've got an electric...
I've got it sped up a little bit. The guy is really... he talks pretty fast, so it's really not bad at normal speed. But, of course, I am trying to save a little bit of time.
Current that's flowing through the wire, making the light bulb glow, and flowing back into the battery. And then, a few years later, we introduced the concepts of there's a voltage here, and there's a resistance in the light bulb, and then a current flows through here that's determined by the voltage and the resistance.
Yes, but the resistance really isn't just resistance. It's resistance for a cause, which in this case, producing light and heat. And so we know it's not nothing, the resistance. We know the resistance is isn't just resistance to flow. That's not why things happen. Why things happen is because it's using the stuff, and that's essentially the resistance to the flow, is the use of the energy.
And it's actually almost exactly the same thing.
I mean, after traveling the thing that's using the flow, the voltage drops. So it's much like a water wheel or some other mechanical device where you pour something in, some of the energy is taken away, and the water that falls off the bottom of the water well doesn't have nearly as much energy as the energy of the water that came out the top. So you've taken the energy out of the water, you've taken away its velocity, and just created water that has very little velocity.
Magnetics. Let me show you. So I have a little magnet between these two pieces of steel And then we've got a steel track here making a circuit and a compass just to show what the field is.
All right, so this is so, in my opinion, not, this is right for the wrong reason, or it's not even right, so I have to say it's wrong for the wrong reason. Attempting to turn magnetism into circuitry is, I think, a big mistake. And just this whole diagram, this whole idea of bringing magnets down, having an air gap, and he really emphasizes this in the math. And you could defeat this argument fairly easily by just straightening those two bars so that they have an infinite air gap. And you won't change how much magnetism you'll get out of the end of the bar. So I could just have them go straight, and it's not going to hurt the magnetism at the two poles at all if I do that. Now, obviously, the smaller the gap, the more I'm having the influence of both magnetic poles at the same time, so I'm going to measure something different off the poles. But if I measure right on the poles, if I measure right on the metal, straightening those bars will give me the same readings as having them bent this way. So it's just wrong in theory. The error doesn't have anything to do with this. It's just wrong.
In this gap here, and then I've got another magnet here just to pull the compass sideways so that we can see when there's no field. And so if I put the thing in here, you can see the compass needle moves, of course, and if I turn it around, it goes the other way. Nothing too shocking just yet. But what to notice is that if I hold the magnet out here and turn it, the compass moves a little bit because the magnetic field can even go through the air. But if I put it into this steel piece, the magnetic field has a much easier time making its way out to the compass.
So kind of a bizarre way to state the truth, as if the air was somehow a bad conductor of the magnetism, and the magnetism is radiating. I mean, it's radiating, and all you're doing is saying, well, of course, if I have it connected to something, I'm going to pick up more of the radiation. It just seems logical. So further away I am, obviously I'm going to have less effect. So the more I'm not connected to the conductor, so to speak, or the thing I'm trying to magnetize, the further away I am, the less effect I have. But the closer, I'm more effect. So again, it's sort of a deception that the air is impeding the magnetism when the magnet's going to excrete that energy regardless of what's there. It doesn't care whether it's air or a conductor or whatever. It's excreting the same magnetism regardless.
And so to notice, the same exact quantities that we get in electric circuits apply to magnetic circuits. We essentially have something like a voltage source, we have something like a resistance, and there's actually a flow through here.
Yeah, so just really deceptive. All you're doing is changing where the end of the magnet is. And I don't exactly understand why his magnet is shorter than the two pieces of steel, or why there's a separation and you use two magnets with steel in between them. I don't know why exactly he's doing that, but clearly when you connect two magnets, and a magnet to a steel bar magnetizes, and to some degrade in the overall magnetism, eventually it will magnetize, and the end will have a magnetic effect, but it's going to be less than what it started with. And it's because it takes some energy just to turn all the domains, but it's just the magnetic the magnet is magnetizing. So clearly that's all it's happening. It's just flipping the domains, but it can't do that infinitely. There's a resistance in the metal, so if I make the piece of metal 10 feet long, I'm certainly going to get a lot less magnetism at the end.
A quick note about terminology. There's actually quite a lot in the field of magnetics, and it makes it hard to understand because there's just so many new terms. And so I've tried really hard in this video to not introduce terms that aren't necessary. But unfortunately, when you go off and search for more information on the internet, they're going to crop up. So we're going to have to cover some. Like, for example, in an electric circuit, we call it resistance when there's an opposition to a flow of current. And in a magnetic circuit, we call it reluctance. And so the trouble is that if you go searching for stuff like magnetic resistance, you won't really find it on the internet. You have to search for reluctance.
So, and again, it's a completely different thing because no work is done. Resistance does work. Reluctance is not doing as obvious a kind of work. You're not gonna. You're just essentially using up the energy to magnetize the metal. Period. and that's what it's going to use it up.
I'll do my best to describe each term as it comes up, and keep in mind we're trying to keep it minimal, and I'll always do my best to describe them first. It helps a lot to visualize what's going on in here. So I took the magnet with the 2 steel pieces out of that circuit, and I'm just going to sprinkle some iron filings on here. And you've definitely seen this demo before.
Right, and he's going to give us some more cliche wrong answer to the question of why it happens. So, so you can sort of get the idea. It's not a great image.
But the thing that's important to note is that there's sort of field lines flowing out of the ends and making a circuit, even in air, right?
So it's like making a circuit, which it's not doing at all, and they don't line up. You'll get breaks in those, lines with the stuff. There's no appearance that it wants to make a complete circuit or needs to. The little bits are each individually just doing what a compass needle would do, which is turn to the field as they become magnetized. So when they're in the presence of the energy being disproportional, that is, one side of the magnet's creating one effect, the other side is creating another effect, and with ferromagnetic material, stuff that can sense that, it itself starts aligning. So the little domains inside of those little iron filings start lining up with the magnet, and that's all that's taking place really, is the magnet is saying what's the strength of the field from these 2 sides, and because of friction the stuff stays out there in these lines, and as the lines get denser they themselves are magnets. So I've illustrated before, but I'll illustrate again in a moment.
Everything is an electric circuit, everything is a magnetic circuit.
So again, a magnetic circuit, I think, is just horrible rhetoric. It's like calling a light bulb a light circuit. It's just wrong. Okay, so if you could make a dipole light bulb, red and blue, let's say, so it shot red and blue light, that's how you should see the magnet. And then you can understand that there could be materials that have little red and blue light sensors, and that those sensors line up opposite to what they see. So the red sensor likes the blue, and the blue sensor likes the red, and so they see it having a polarity, and the sensors just line up to meet the polarity. That's all that's happening. But you wouldn't call it a light circuit.
And the trick is that electricity really, really doesn't want to flow through air, so we can usually neglect it in thinking about electric circuits. It's actually very fortunate because all of our circuit boards require air and insulators to work properly.
Well, the problem with that theory is they really do. Electricity really likes air. Frankly, if you get the voltages high enough. So at a high enough pressure, air is fun for electricity, and so it's at a low voltage, at low pressure, air is a monstrous cavern to jump. But when it has high pressure, like a little rocket to jump the Grand Canyon or something, it's like saying, I don't care, Grand Canyon, Sman Canyon, doesn't mean anything when it hasn't, big enough springs on its feet to jump over it.
But with magnetics, even though the field doesn't really want to go through air, we'll talk about what the exact numbers are later.
So again, the field is never affected by air beyond the fact that you can understand that there's some atoms in the air, and those atoms are going to absorb the energy of the magnetism like gravity or like anything else, and they're going to get in the way. They're going to degrade to some extent. But magnetism plows through stuff pretty well. It plows through cardboard or paper or wood or your hand even. You can put a neodymium magnet on one side of your hand and pick up nails with the bottom of your hand. So it does plow through material quite well.
It can still make it, and so there's a magnetic field flowing around here.
So again, there's a magnetic field flowing around. So this is just so ingrained into how physics is taught, and it's it has this crude appearance, of lines connected, but shouldn't we know that might be a false indicator, that that's not exactly why it looks that way, and that a lot of things are going to cause that effect. A lot of things could cause the effect. So again, it's this jumping too quick a conclusion, without thinking about what other possible explanations there could be for why these filings are behaving the way they are.
We could do the analysis and figure out just how much is flowing through there based on the reluctance of air. So
yeah, so that's just in my opinion wrong, and most of this video is going to have that assumption built into it, and I think it's just wrong. The air has nothing to do with any of this. Again, I could just straighten his U. I guess we'll go back to that eventually, so I could just point it out again. And you can just figure out for yourself that you're not going to change how much magnetism went through the steel bar by making it straight or making it crooked. It's going to be the same amount. Alright, so to the drawing board, I believe. We're ready for that. Alright, so the magnet. And as I have pointed out many times in many videos, yeah, colors. Anyway, all right. What's really happening? Magnets are just made out of little magnets. So essentially, the reason why ferromagnetic material is ferromagnetic is because it's got atoms that are already dipolish. Okay, so they're already doing this green-orange thing, and all you're doing is lining them all up exactly the same way. And so this thing called a magnet is just a filter. So essentially it doesn't have any energy in it. So he's going to imply later that they put energy into magnets. And no, it takes energy to align these domains, but there's no energy when the domains are lined up. It doesn't make the magnet energetic in any way. It just changes how external stuff, okay, is affected. So yeah, there's no way of doing this without giving you some of my theory mixed in. So you have to understand that their thing we call gravity is a particle force like photons. Okay, it's moving the speed of light force. Everything, all the things moving the speed of light are made of the same stuff. And there's just two versions of it. There's an electron force and a proton force, in the sense that they are they react differently. So I really hate to go over that again, but I might have to. You know, I might have no choice. You know, the simple argument is there's the electron, the blue force, the red-green force in this case. Okay, sorry, I got that drawing way too high. But anyway, so when the force hits it, it essentially reflects the green force, and when the proton force hits it, the orange force, it leaves perpendicularly. So that's, you know, one of the perpendicular dimensions. And vice versa for the proton. It reacts exactly the opposite to the electron force. It leaves perpendicularly, and so anyway, so the idea is when orange force goes into a magnet, okay, no matter where it goes in, it ends up coming out one of these out of the orange end. It ends up being perpendicularly bent if it comes in here and comes out the orange end, and all the electron force comes out the green end. And you can see an obvious one obvious fact would be if a green hits this green part of the magnet, it's just going to reflect. So obviously it's coming out right back at you. And if an orange goes in, it goes out this end. So that's what a magnet is radiating. So it's taking an external force and magnifying it, which makes the word convenient, magnetism, even though magnesia is why it's called a magnetism, where magnetism was first discovered, apparently, or one of the places. So the magnet is not itself generating any energy at all. There's force coming into it, bent space, if you want to call it. I don't really care. An invisible force comes in, an invisible force is filtered by the magnet and goes out, because the magnet is essentially at equilibrium. Okay, so it's whatever goes in comes back out. So, but it comes out filtered. So one end is producing force that reflects off electrons, one end is producing force that reflects off protons. And by reflect, I mean it gives them momentum. So a thing I should have pointed out is the perpendicular change doesn't involve any momentum exchange, and the reflection does. And so if you take the, I forgot to make an eraser, so I have to contrive one, spittle and such. I guess I could pour some drink on it. That might work better. That's just music to clean the board by. Yeah, the record was still playing, so I let it finish. Anyway. Okay, so what last point do I want to make here? Okay, so the field lines. So understanding the what's creating the field lines. So field lines would be created, like I said, if I created two light bulbs doing the same thing, creating two different kinds of radiation. So the radiation is bouncing out of this thing polarized. That is orange coming out of one end and green coming out of the other end. And as stated, all the little filings he dumped on there instantly start lining up with the domain. So just like when you see regular magnets and you hold them next to each other the wrong way, you can feel them wanting to turn. You know, they have the force is effective on them. It's affecting them. It's pushing on them, and you know, torquing them. And that's because of the unevennesses of the reflections. Because the force is magnified. So, I mean, if I had another magnet of the same polarity, you could see that the two magnets would end up reflecting incessantly. Okay, you get a ton of stuff caught in here, and there'd be a ton of stuff caught in here, and you'd have insanely high pressure here, because everything reflects. So everything that goes in is getting caught in this reflection. Not everything, but a substantial amount. So this stuff is still coming out in the same rate, but everything here is now time changed in the sense that stuff can stay bouncing back and forth in here for a very long time, and so you'll end up with a maximum amount. Then it starts leaking out, but the pressure will increase as you bring them closer and closer together, because they're hitting quicker and quicker. All right, and the vice versa would happen, so I shouldn't have to do that for you. But if I flip this magnet, you should be able to understand that then the orange stuff is everything in the green side goes into orange, which means it leaks out perpendicularly, and everything orange goes out the orange side. So it's everything leaks out, so you don't get any pressure. So the pressure out here is the pressure that pushes them together. So it's just like gravity in that sense. But don't want to have to explain gravity in this video too. But anyway, all right. So the filings are doing the same thing. They're going to want to line up to the low pressure. Okay, they're going to want to move into low pressure. They're not going to move into high pressure. So they're obviously, the little filings are going to start aligning themselves to the strength of the field. So they're going to want to have as much of their green end as possible facing the orange side of the magnet, and as much of their orange end as possible facing the green end. And the catch is the arc they're going to end up taking, okay, each magnet will line up in a way that, yeah, it's going to look like a circuit, but there's no circuit here. This is just each individual magnet saying, how do I line up to maximize my exposure to this magnet in terms of being having the most of my orange facing the green and the most of my green facing orange. And the fact is, it'll line up something like this arc. So that's how the compass needles will line up. And it just has to do with how strong this force, the closer you are to it, the more effect it has, the more diluted this effect, so the more you end up being lined up straight. So, I mean, a magnet facing here is going to line up, perfectly straight, because technically all it's seeing is complete orange, and at this orientation it has no exposure for orange to orange, so it's not getting any negative effects, and it's just getting all positive by lining up this way. So they line up straight until they start to get to these edges, and once they get close to the edge, then they're feeling more of the green pressure and they start to bend towards the green. So that's all they're doing. Now the catch is they all line up obviously with the same orientation as this, except exactly opposite. So they line up as an opposite magnet, and this itself becomes, when they stick to each other, they'll stick to each other in the same configuration. The orange ends will be pointing one way, all the green ends will be pointing the other way, and this will essentially just become one big magnet. Okay, this row of iron filings. And so essentially it's just going to be a bunch of little magnets, and it'll just be creating now an opposite polarized magnet. I think I've said that correctly. Let's hope. And so the trick is that what decides, see, you just end up with one big field line. If it wasn't for the fact that each one of these, when they're starting to line up, each one of the successive, when they're lining up at different locations, these magnets all end up being of the same polarization. So each row has the same polarization. And so you can sort of see that when they first start to line up, they're going to start repelling. So you end up with high pressure here. So each line is going to repel each other by the strength of their density. And so the more dense the line is, the more magnetism it's going to have, the more separation there'll be. And the finer the iron filings, the closer they can be, because they're not as hostile. But like I said, the more iron filings means more distance between the lines, less iron filings, less distance. But these are clearly, so this magnet is still attracted strongly to this one, because this is the strong magnet. This is your original magnet. This one made of iron filings is much weaker. It's like 1/10 of the 1/100th of the strength of the original magnet. So obviously they're still arranging to this magnet, but they're reacting to their neighbors, so they have to have a distance between them. So that's what just creates all the lines. The lines are just the fact that each one of those lines has the wrong polarity. I mean, they're common, the same, and they're repelling, but they're all attracted to the main magnet. So it could be understood through this model that there is nothing flowing here. There's nothing going through here at all. There's no movement of anything. Nothing's traveling through these magnets. They don't have to be connected to each other. Little iron filings don't have to connect to each other. They obviously become a more substantial magnet in terms of size if they can start connecting and getting thicker, but they don't need to. So you can have huge breaks in here, and all of these little compass needles will still act exactly the same way, because they're really just individual magnets in the end, and it's the individual magnets that are creating the effect. And in ferromagnetic material, that's what's happening inside the material. So you can get ferromagnetic material that's really the little bits of magnet are separated from each other, so they don't even have any ties to each other in terms of creating a sympathy. So their magnetism can be radically changed without them having residual effects of having a whole bunch of lining up, and that means the whole mass has to be moved, and that can take more energy to move domains that have sympathy with each other. Domains that are connected to each other essentially would be harder to move than domains that are all flipping independently. So the more independent you can keep them, the easier it is to change them. and clearly the little iron filings are fairly independent. Their domains can be changed easily, and so they will just orient to they'll force the material to move. See, I'm saying the domains are moving, and it's kind of a wrong way to think about it, because in a sense the domains are aligning, and that alignment is forcing the whole material to move. So anyway, it's majority rule kind of thing. Once you start moving enough of the domains start turning, it starts to turn the whole material substance. Alright, so I think that's enough of that. I think. So I'm just presenting that there's other models, other mechanical descriptions of cause and effect that don't show any of this idea of a current of energy in the magnet. The magnet has no energy. It's just the same material. Whether you magnetize a piece of steel or you have an unmagnetized piece, you have exactly the same energy potential. The atoms are not super atoms now or some other kind of thing. And all you've done is changed what it can do to some other force that's coming in. So it's almost a way of proving my theory, is to just point out that all you're doing is making it into a filter. And what is it filtering? It's filtering the biggest force in the universe, gravity. The only force in the universe. Light is gravity. Magnetism is gravity. Electricity is gravity. It's all one force, moving the speed of light. Alright, hit the right button, Gary. Or something like the right button. That appears to be the right one, so moving on.
Let's put this into the circuit so you can see how that changes the field lines. Okay, now we'll try the same thing with this in circuit.
Alright, so this is pretty shabby as an example, but whatever. Now, what he's done now, so you can see there's gaps, okay, between the magnets and the metal. And but the only thing that's changed, why are the filings changing a little bit in how they line up, is only because now you're magnetized the metal. So there's now another magnet in the environment. So if I bring another two magnets together, I change the field. If I turn them this way, I change the field. If I do it this way, I change the field. So he's just introducing two more magnets into the field, and of course their poles are opposite. So now you'll have a green pole next to an orange pole, and so where the little bit before was saying, oh gee, this is all green this over here, so I'm going to go towards green. Well, now it's got a big hunk of orange right here. So now it's saying, oh, I can't go that way because, you know, that isn't all green, so I got to go some other way. So of course it's going to change the field. Duh.
Notice that there's quite a bit less activity here, and the reason is that these steel pieces are pulling away the magnetic field.
Alright, so it's not pulling away any field at all. It's introducing another field. It's introducing another magnet of exactly the opposite polarity, which is obviously going to say to the little iron filings, the old pattern isn't going to work anymore because green isn't green anymore. Green is now orangey green.
Easier for the magnetic field to flow through these low reluctance pieces of steel rather than flow through the air.
Okay, it's just, sorry, that's just, no way is that correct. Okay, so it has nothing to do with flowing through the air. And the iron filings are filling the gaps of the metal, obviously, because that's where the strongest field is. The field is migrating right into the steel in the sense that the strongest amount of polarized field, that is, a bunch of green energy is pushing in one end, a bunch of orange energy is pushing in the other end, and that's automatically lining up all the domains in that piece of steel to that orientation. And as each domain flips to become a magnet, so as the ones here flip, the one behind it sees that flip and says, I'm flipping, and the one behind that sees that flip and flips. So it's just a domino where the domains are seeing the tail, they're seeing the changes. So the change moves with a great deal of efficiency through the piece of steel. I don't know. I don't know I can't tell you how actually long you could make this piece of steel. But again, if you made 6 inches and then you made it a foot and then you made 2 feet, you'd still be measuring. If you measure the Gauss meter, you measure the amount of magnetism at the tip. There's probably a relationship. It probably isn't the R inverse square law. It's not even the R law. It probably diminishes by some, whatever, 15% per foot or something. It's probably more than that. 30% per foot, 40.
So, there's two camps on whether you want to anthropomorphize physical phenomenon, but you could say...
Well, it seems to me you want to electrify all the physical phenomena. So you're basically trying to turn the magnet, number one, into a producer of energy, which it's not. And then you're not understanding how it transmits the magnetism through the piece of steel, which is it's transmitting it by flipping the domains inside the steel, by the compass needles inside the steel is full of little compass needles, and all it's doing is it's changing those compass needles, and as each compass needle changes, the one behind it says, oh yeah, I'm going to line up with that compass needle, and they're all going to line up with each other. But it's so distant from the flow of electricity that it really shouldn't be viewed the same way.
The magnetic field would rather flow through the steel than it would flow through the air. Or you can...
Okay, again, you can't control it. So there's no rather. The stuff will, it's a radiant force, and you have no control over it. There's no knobs you can turn. There's no anything. So you're either making a field or you're not making a field, and you can have two fields that are causing two different effects. So we're back to that magical superposition word. The forces can't interact with each other at all. So, but you can have two different forces affect some third thing in the environment, and the two forces will have their independent effect, and they'll be additive or subtractive. Okay, but they can't affect each other in any way. So you can't change what the magnet's producing. You can only produce another field that mixes with your field and now creates a different field. So you can have two of these magnetic light bulbs. They're green and orange, and green and orange. Now if I only have one, then I'm going to have a very clean, nice field. If I put another one in the field somewhere, like this way, you can understand that from some locations the light's going to look like orange, green, brown, let's say. Some locations it's still going to be orange, some locations it's still going to be green. But it's going to be a more complex field, but nothing is going to, you're not going to be able to change what the light bulbs are producing, and their radiation will not be bent. The photons won't be moved. So you're not going to change what it's producing, you're only going to introduce another field.
Just think of it in terms of reluctance. The steel has a lower reluctance, and so it conducts more of this magnetism than the air around it.
So that's just so wrong. I mean, just so wrong. This is, like I said, if you thought of it as light, you would never buy that argument that the light can choose, oh, there's a fiber optic cable over there, I'll go through that. Okay, I'm going through this. Let's say I had some kind of opaque stuff here, and it's saying, I don't want to go there, that's opaque-ish. I want to go through that cable over there because that's nice and clean. Photons can't do that. So that's just not, that can't be happening, and there's no evidence that that's happening. And in like I said, every break in your field lines is demonstrating that's not happening. There's no preferences here. Photons can't do that. And this magnetism force is a photon force. It's moving exactly the same speed as photons, exactly the same speed as gravity. This is a little force bit, a quantum of energy that are shooting out of this magnet, and they happen to be polarized, orange and green.
And if we took these gaps out and made it perfect, we would have even less field leaking out into the air.
So again, you'd only have more field being produced by the pieces you're eliminating the air. But if you connect the magnets to the steel, you'll end up getting, your field lines will end up looking pretty symmetrical again. So if you actually get rid of the air gaps, which are just degrading, they're making your new magnet the wrong polarization. So by putting the things together, you'll end up making a more continuous magnet, and so then the field will change because now you've actually connected the magnet, which means it becomes, so if I take a piece of steel and I have it away from a magnet, okay, so I have a north pole. Let's see how to illustrate that. I don't really want to have to draw it because I shouldn't have to. And I put another magnet, a piece of steel next to it. Well, the steel is it's going to go orange. Where's my green cap? That would solve this problem. Okay, this is the way to do it. Orange cap, green cap. Okay, so here's your one end of your magnet. And so if you put a piece of steel here, you're going to end up creating this opposite magnet. Okay, it's going to be green, orange. But if I connect them, all right, then it's the little domains are going to take over, and it's going to have the impression of kind of creating the orange-green magnet again. So you'll extend the magnet out further. So you'll be radically changing the magnet by bringing it just close. You're creating an opposite magnet. By connecting it, you're extending the original pole. So you're making it a North Pole magnet again, instead of being North Pole, South Pole magnet versus South Pole, North Pole magnet. You'll be creating one big magnet again.
So we've shown that a magnet acts like this source of magnetic force. It's kind of similar to voltage in an electric circuit.
All right, it's not similar, and it's really a bad comparison. And sorry, wrong.
But there's an important difference between a magnet and a battery. A battery is an electrical energy source. I mean, it's converting chemical energy into electrical energy, and we're actually pulling electrical energy out and burning it up in this tungsten filament lamp.
And by electrical energy, you're essentially saying pressure. So we've got pressure in the battery. We've pressurized some atoms, and now they're going to depressurize. So we've put them in an unnatural state, compressed the springs, so to speak, and we're just going to take back that pressure. So it's like it's again, we're back to the little reflections. So if I can move the paddles together and create a lot of pressure, I create energy that I can use later, expansion energy. So if I compress things, there's energy trapped in the compression that I can release anytime I choose to uncompress.
A magnet is not an energy source. A magnet is much more like a compressed spring. So
I say a compressed spring is an energy source. See, again, it's just kind of so wrong. When you charge the battery, you're compressing the chemical springs. You're pressurizing the atoms, and so again, I'm not picking on him. This is how physics is taught, and it's just, I think it can just be understood that this is not the right model for magnetism.
So at the factory, they started with a piece of material that was not magnetic and put a lot of energy into it to make it.
Okay, so he just said put a lot of energy into it, and later in this video he's going to take a nail, swipe it once with a magnet, and turn it into a magnet. So obviously you don't have to put a lot of energy in. Now if you want to make a permanent magnet, yeah, you do, because you have to create a rigidity. You have to melt things into their condition. So you're creating domains that can't move, by less movable. And so you're making a permanent magnet. So you end up creating a magnet where you did all this aligning, and now they have two properties. They've been pre-aligned, which gives them a rigidity. So if you take a bunch of magnets and stick them together, they don't fly apart easy. You have to really rip them apart. So once you do that to domains, you do the same thing. You create a domain that isn't going to change easy. So if you melt the domain, the structure in, it has much more durability. But one whack of a hammer and you can knock it all loose again. But clearly not a great deal of energy has to go in to get the effect of magnetizing the steel. Creating a permanent magnet, yes, energy has to go in, but you're not getting that energy back out. And he's almost implying that you're getting the energy back out. That the energy you put in to make the magnet is the energy coming out of the magnet. So again, see, they don't have any, they have no clue. You know, conventional science, physics, and, you know, all these people that play with magnetism, they have absolutely no clue where the energy comes from. And there's real energy. I mean, there's stuff coming out of the damn thing. It's a light bulb. It's on. Okay, green, orange. It's doing something. But they don't understand that all it's doing is filtering the energy that already exists. And they don't understand that all that energy exists because they bought some stupid bent space nonsense to explain gravity. So they don't understand that there's a whole bunch of energy in the universe that you can tap. And magnets are tapping it by filtering it. So you can just see the whole cascade of these wrong assumptions. Once they accept something, a wrong model, you can just see how corrosive it is to everything else. Accepting bent space just broke all of their mechanics, because all of these things that happen, you don't have any explanation for where the energy comes from, because you took the biggest pile of energy in the universe out of the universe.
Into a magnet. So think of this as kind of like a compressed spring.
So think of it as a compressed spring that unsprings literally forever. It's a filter. See, filters can last forever, right? You can make a filter that's just an arrangement that can stand forever. You know, you could say the Empire State Building is a filter in a way. It has a certain shape and configuration. When light hits it, it'll reflect a certain way. So in a way, it's filtering the light that hits it. And that could last as long as the building can last. There's no, it doesn't cost it anything. The Empire State Building doesn't have to use any energy to be a filter. So a magnet doesn't use any energy to be a filter. Once it's a filter, it's a filter. It can do that forever. It doesn't run out.
Providing force for us because it's a compressed spring, and we can.
So again, it's a compressed spring. The battery is a compressed spring. The magnet is not a compressed spring. Nothing. There's no compression. There's no energy leaking out slowly. There's no wound up something that leaks out slowly. There's no radiation inside. There's no molecules degrading. There's no decomposition of atoms. There's no radioactive decay. None of that is happening. It's a filter.
Squeeze it harder, or you can
squeeze it harder. Squeeze it harder. You can't squeeze a magnet harder. You can't do that.
The energy out, but only once. So it's much more.
You get all the energy out, but only once. That can't happen either. You can whack it with a hammer, break the filter. You can hit the Empire State Building's facade and crumble all the exterior concrete, but you can't. You know. There's no destruction of energy anywhere. You can't use it or destroy it because it's not in the magnet. The magnet's just filtering the environment.
Or like a small storage vessel that's filled up at the factory, and you really just.
So he says filled up at the factory. So it's like a battery. He keeps comparing it to a battery. We know batteries run out. We know compressed springs run out. We know all of those examples completely fail. So, you know, like I said, this guy is really smart. And it just seems like he's saying this stuff because this is what he was taught, and it just doesn't make any sense at all.
Can't get, you know, forever energy out of it, of course.
Of course, but you're not explaining. You can't get forever energy out of it, of course. Yet there's no example of the magnet that ran out on its own without whacking it with a hammer or without heating it too hot, without doing something destructive to its molecular structure. Where's the example of the magnet that just ran out of magnetism? I just ran out. I only had so much and I used all my magnet gas. There's no example. So it's like you say, he just said something overtly. Like, well, no magnet can last forever. Where's your evidence that they can't?
Okay, let's try something else. So instead of the permanent magnet with the two pieces of steel, I have just a single piece of steel here with about 50 turns of wire wrapped around it. And when I close the switch here, about 3 amps flows through there, and you can see the compass needle turns when I put current through there. So it's as if this piece of steel is becoming a magnet when we put power through, and when we stop.
Yes, well, everybody already knows that. That's exactly what's happening. Yes, the steel is being magnetized. Now the coil, I've been over how the coils work in the sense that it's, you know, the inside it's doing a lot more reflecting. So it's like having magnets, you know, opposing each other, and they're just doing a lot of reflecting, and so it's maximizing the amount of pressure. inside the coil versus outside the coil. It's probably worth illustrating to some extent. Probably. Well, we'll get to it because we're going to get to paramagnetism.
Putting power through it is no longer a magnet. You could almost say it's an electromagnet, right? Okay, so...
yes, so it's a magnet when you have the power on. It's not a magnet when the power's off. Now, if you heated that little piece of steel and then turned on the magnet, you would make it into more likely make it into a permanent magnet, or more permanent. And there'd be some residual magnetism in it anyway if you banged it while you had it on. So if he just even tapped it, hit it while he had the power on, he'll have a lot more residual magnetism, maybe 20%.
We'll try it with a different material. Let's try a piece of brass. Okay, I'm turning it on and off, and you can see it's the same 3 amps. And we'll zoom in on the compass so you can see this a little more closely, but there's barely any movement.
All right, so he doesn't really get into the subject, but I mean, that's obviously can't work because the brass is paramagnetic. So it's doing exactly the opposite of what the magnets are doing. In a sense, it's creating an opposite magnetic field. It's not one that's lining up. It's lining up wrong. So it can't magnify any forces. So I have to go back to the drawing board and such. I might do this in 2 parts because I am getting a bit tired, but we'll see how it goes. Racing song. It's an actual racing song with lyrics and such. Yeah. But it's not a very well written song, so you'll just have to accept that it's not a very well written song about a racing. There. Alright. Alright, so the coil, thing to understand about the coil is that the magnetism across the coil is actually happening across the coil this way. The wire itself is becoming a magnet this way and this way. So in a sense, you could think of it as from any view you look at it, no matter where you look at this wire, the wire will actually be magnetic on one side, forward side will always be orange. I don't know how to do that without making it look stupid, but so it's the inside is going to see magnetism pointing in a direction again. All the little magnets of this coil are all lined up in a direction. So it's all, orange, green, orange, green, orange, green, orange, green, orange, green, for how the wires are creating the magnetism. And so as that goes into the coil, obviously when the green stuff hits the orange stuff, it ends up going perpendicularly, coming back out the green. So you have a lot of internal reflections inside the coil. So if this was inside the coil, you could sort of understand that everything that's being produced, goes across, hits something, and the argument is that if it hits orange, it's going to do a U-turn. If it hits green, it's just going to reflect. So it's either way, all the green stuff and all the orange stuff is going to be filling this coil and making it a magnet, and making it a very strong magnetic field in there. So now, then when you put a piece of metal in, the metal is seeing this fact that there's an alignment to the field. It's always more orange. If you looked at it from this way, it would look very, if you looked at it this way, you would see green, 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 green coming out of the wires. And if you looked at it this way, you'd see orange, 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 orange coming out. So, and so the steel is going to end up lining up in sympathy with that field. And so this is going to be the orange end, and this will be the green end. All right. Now the problem with paramagnetic material like brass or aluminum or all that stuff, when it senses the field, the pressure, it reacts completely different in the sense that you're not turning magnetic domains now. So the brass isn't full of little compasses like the steel is. So the steel is full of little compass needles that just line up. But the brass doesn't have any compass needles. So what you do when it senses the green pressure, let's say the electron pressure, it means it compresses the electrons, and when the orange pressure hits it, it expands the electrons. So it ends up changing the polarity of the atom by compressing or expanding the electrons. And what it ends up doing is creating the opposite field. So it's like having the coil and then putting an opposite magnet in it. It just isn't going to work, because now there's not going to be the same reflections, and it's not going to magnetize the paramagnetic material. It's just going to create a bunch of what's the right word for it? It's just not going to work. Yeah, I don't think I have to go into it any deeper than that, just to explain that there's no dipoles inside the paramagnetic material. You're not just aligning dipoles. So it's really hard to turn the paramagnetic material into a filter, because you don't have any dipoles to line up. So all you can really do is screw around with its surface and cause surface effects, and you can cause electricity to run through it, but you can't make it into a magnet. It just doesn't do it. All right, back to the video. Undo this, and don't hit that button. No.
Okay, now I'm going to switch to another third type of material. This will be a piece of stainless steel. It may be hard to see, but the compass is actually moving a little bit more than the brass, but less than the steel. So let me switch to a...
Yeah, it's kind of using a tricky thing. You know, it's sort of a tricky one. The thing with stainless steel is that it's, again, the high temperature thing, and so the domains can't align because they've been broken by heat. So they're all locked in random positions, so they don't have any magnetic orientation. But you probably could, well, I don't know. Yeah, I won't say anything I don't know anything about, but stainless steel breaks the ferromagnetic properties of the iron in the steel.
Meters, so we can actually put some numbers on this instead of just looking at a compass moving. So I've got this magnetic meter that I got from Amazon, and it reads off in units of millitesla, and this is kind of the sensor on the end of this probe here. A Tesla is a unit of magnetic flux density. So it sounds complicated, but really, if you think about these field lines connecting one side of the magnet to the other, the flux...
So again, connecting one side to the other, and as I've tried to explain, obviously the green light isn't trying to connect to the orange light. The little sensors that are lining up aren't trying to connect. Nothing's doing this connecting thing. It's an illusion. It's a byproduct of the elemental function. The elemental function is not connecting. It looks like a pattern, but the pattern has nothing to do with any agenda of moving current or something.
Are the lines themselves, and the density is just how closely packed they are together. So the Tesla is used as a unit of describing kind of how intimidating your magnet is. An MRI machine is like a 1.5 Tesla or a 3 Tesla machine. A large neodymium magnet could be something like half a Tesla at the surface.
Right, so it's just a way of, if you were to compare it to light bulbs, it's just a way of measuring the wattage of the green or the red.
And so here's a couple of them stuck together with a little space in between. If we put the probe right on the surface, we're getting about 460 millitesla, so about half a Tesla at the surface. Now the interesting thing is if I turn the probe 90 degrees, we get almost zero. In fact, I can turn it to a point where in fact it is zero. And I'm just turning the probe on the surface.
Right, so you're just turning the probe, which means you're putting it in a position where it senses no torque. So you're lining it up essentially with the field. So once you line it up with the field, it's perfectly happy and it senses no torque. So the way it's reading the strength of the magnetic field is to line up opposite. So you're just basically saying what's the opposite strength, which is the maximum strength would be being aligned opposite. So it's like aligning the two magnets where you have orange pole against orange pole, and so you've maximized how much repulsion there is, and then when you have green pole on green pole, you've minimized the amount of pressure so that it's most comfortable. So you're just measuring, you're just taking a compass needle and putting it into the field the wrong way, exactly the wrong way, to see how much torque there is, and that's telling you how strong the magnet is. How much torque is there to flip? The flipping speed, the flipping energy, whatever you want to call that, is what the meter is reading.
Surface here. This makes sense because this probe only measures magnetic flux in one direction, this way.
It can only measure, so it's doing what all the, you can't measure a magnetic field without using a magnet. It's just the rule.
Kind of see there's like a little dot on the surface there, and that's the sensor itself. And on the other two faces, there's no dot, so it only measures in this way. And since the magnet is polarized so that the north pole is this way, if we put the probe so that it's cutting through all those, so that it's lined up with the magnetic field, then we get the full reading. But if it's 90 degrees off,
so he has it exactly opposite. He's saying that, oh, we get a big reading when we're lined up with. No, when you're exactly the opposite alignment is when you get the big reading. You get no reading when you put it comfortable. You've taken the green, orange, and then you've made your probe green, orange, and it's nicely aligned and saying everything's fine, no torque.
Get nothing. So anyway, so about half a Tesla at the surface, but if we move away from the surface, the reading goes down really fast, really fast. So for this far away, and the reason is that air has high reluctance to this magnet.
So again, it's a, I don't know why he's saying this stuff, because this is just the inverse square law. Air has nothing to do with it. There's a, just as light radiates. So the magnet radiates by the r cubed because it's a dipole. But let's say he could just take that top pole off, some way, disconnect it. It would be an r squared rule, just like a light bulb. And so that it doesn't care about medium. The air has nothing to do with it. Same reading in space, same reading in any medium that doesn't have a bunch of magnetic material in it, a bunch of polarized atoms. So as long as you're in a medium that doesn't have a bunch of polarized atoms, your field is going to move at a certain rate, and it's going to move with a certain density at distance. And magnetism is not easy to block. You can only block magnetic fields essentially by creating another magnetic field. And you're not blocking it, you're just diluting it. Say if you have a bunch of green, right? And it's radiating through something. Well, if I put another magnet in front of it that's producing orange, you can get it that now I'm going back to the 50-50 mix. Now I'm going back to the original field. I'm unfiltering, right? I'm taking away what the filter did. I'm undoing what the filter did. But that's the only way you can destroy the magnetism, is to undo what the filter's doing, in the sense that put the light back to being mixtures of green and red.
Magnetic flux. So even though the magnet is trying to push a lot of magnetic flux through the air is not very good at conducting it.
So I don't know why, it's just, so it's trying to push flux through the air, and it's trying to make circuits, and none of that's happening.
And that's why this drops off so quickly. There's just not a lot flowing. So when you measure...
So it has nothing to do with the drop-off. Like I said, the drop-off is just standard R 1 over R rules. 1 over R, 1 over R squared, 1 over R cubed. It's just the standard law of straight line radiant forces. All straight line radiant forces. That is, all things like a sun shooting little rays out from all directions. All of those things obey one of those R laws.
For a magnet, you have to specify where this flux measurement is happening. Okay, so let's measure the little electromagnets that I've made.
Okay, so yeah, we'll probably end here. I don't know if we need to come back to it. So again, it's just going to measure there's no electromagnetism in the stainless steel or the brass, so there's no point in measuring it because it can't produce any. So anyway, and then he gets into a bunch of, now then he starts applying the rules of electric current to the flow of magnetism through, and again, it's just wrong-headed. And as I pointed out, you can sort of logically understand that when he has this little U thing of metal, you're not changing the magnetism of this either pole of that piece of steel. If I made the steel straight, you'd understand that the magnetism would read just as strong as it does bent, and the air gap has nothing to do with anything. And he does a whole bunch of mathematics implying that that air gap has some kind of significance when it can't possibly have any significance. Alright, so anyway, till the next video and such. So you know, I mean, I don't mind coming back to this, but like I say, if you watch the rest of the video, I'll put a link below. It's, you know, it just gets into a lot of math based on these wrong assumptions. So, but he does have a hell of an oscilloscope and all that kind of stuff. But anyway, I really think that's enough. I think I've made my point. But I really like to find somebody like this guy, really smart, to have these conversations about these fundamental assumptions of physics, and whether they have any evidence defending them or not, whether there's really any evidence that there's any movement around a magnet, any currents flowing, any of that crap. Okay, so till the next time and such.